Excellent. There we go, and there we go. And let's go here. Oops.
Titrations can be used to determine the concentration of a specific ion in a sample solution. Here we'll see how titrations involving precipitation reactions work.
Okay, let's make sure everything's maxed out here in terms of volume. There we go. There we go. All right. Make sure that's big. Those going.
Here's a setup for a titration of a solution with an unknown concentration of Cl- or chloride ions. This long tube is called a burette. Burette can also be spelled B-U-R-E-T-T-E.
All right, so we are filling in as we go along here. So we have our burette. We have the stopcock, which is also known as a valve.
This valve, called the stopcock, is closed to keep the liquid in the burette. When it's opened,
I'm going to take off the subtitles because I don't know that they're helping, especially when they spell burette buat. Do you want the subtitles on? No? Okay, yeah.
liquid will drip or flow out of the bottom of the burette. In this example, the burette is filled with 0.100 molar silver nitrate solution.
We know the concentration, so that is called the standard.
The solution in the burette is called the standard solution. The standard solution has a known concentration. In this case, it's 0.100 molar AgNO3. The standard solution can also be called the titrant. In this titration, a solution containing chloride ions is added to an Erlenmeyer flask and placed under the burette. The solution in the flask
It's called the sample. Do we know the concentration of the sample solution? No.
is called the sample. It's the solution with the unknown concentration. It can also be called the analyte, because this solution is being analyzed to find out the concentration of chloride ions in it. In this titration, a few drops of sodium chromate solution are added to the solution. The sodium chromate solution is known as an indicator in this titration.
So we have our standard, our sample, and our indicator.
It will change color at what is called the end point of the titration.
Remember, the end point is where the indicator changes color. What do we call the point when the reaction is perfectly complete? That is the equivalence point, also known as the, starts with an S. What can I do for you?
Take a peek. Take a peek.
I don't have a Jacob B.
Thank you for your assistance.
No problem.
Jacob S.
I don't have a Jacob in this classroom. I don't think. We don't, do we? No. Nobody sits beside a Jacob that I'm forgetting? No. Okay.
We'll show you how all of this works. We'll focus on the solutions. We'll dissociate AgNO3 into its individual ions, which are Ag plus and NO3 minus ions. The nitrate ion does not form any precipitates. It's a spectator ion here, so we'll just delete it from our discussion and tidy up a bit. So you can think of the solution in the burette as a source of Ag+, or silver ions. In a titration, we briefly open the stopcock. The solution in the burette drips into the flask, bringing Ag+ ions with it.
I like this little animation. You can see the Ag dripping in, yeah?
Let's take a closer look at what happens in the flask as silver ions are added to it.
Okay, is there anything that you didn't get to fill in that you don't know what it should be? Yeah? What? Which one?
Like on page 8, the bottom part.
The bottom part? Okay, it should say 0.1 molar AgNO3. And I'm not quite sure what it should say beside it, but that's okay. And then we have 0.1 molar Ag, and then we have NO3. NO3 should say spectator. Anyone know what that one above the other one should say? No. Okay, doesn't matter. Not important.
Now we've zoomed into the flask. Silver ions preferentially bond to chloride ions rather than chromate ions.
Did you catch that? The Ag prefers to bond with which of the two ions in this flask? There's chromate and there's chloride. Which one does silver like better? Likes chloride better. Okay, that's going to have a lower KSP. Okay, so it bonds more strongly with chloride. So it's going to react with chloride until all the chloride is gone, and only then will it choose to go with chromates.
This forms the precipitate silver chloride. Because silver chloride is white, the solution turns to a milky yellow color. As silver ions are added, some will temporarily bond to the chromate ions.
Okay, they do that because all these systems are equilibria, yes, but because they are not as strongly attracted, eventually they're going to let go and be attracted more to the chloride.
This will form the precipitate Ag2CrO4, or silver chromate. Silver chromate is reddish-brown, so the solution will turn a slightly reddish color. But silver preferentially bonds with chloride, so as the flask is shaken, the silver ions will leave the chromate ion and bond with available chloride ions, and the reddish color will go away.
Okay, do you see how that's going to indicate it though? Because once all the chloride's gone, it will bond with the chromate permanently and it will turn it red. So we're just waiting for it to permanently turn that red color.
The solution will turn red momentarily as more silver is added, but as long as chloride is still present, shaking the flask will make the red color disappear. Added silver ions will continue to bond with the remaining chloride ions. At a certain point, all of the available chloride ions have bonded with the silver ions.
Okay, so I think we're probably on page 84 by now. Let's take a look. Yep, there we are. Nothing to fill in yet.
Since there are no chloride ions left, any silver ions that are added will have to bond to the chromate ions. The formation of silver chromate precipitate will cause the solution to turn red again. At this point, when the flask is shaken, the red color will no longer disappear. There are no chloride ions available, so the silver will have to remain bonded with the chromate. We say the solution has turned a slight permanent reddish color. This is what's called the end point of the titration. A permanent color change of the indicator signals the end point of a titration. The equivalence point, or stoichiometric point, of this titration is the point where the moles of Ag+ added to the flask is equal to the moles of Cl- that were in the original solution.
Now, in this particular case, this is moles of A equals moles of B, but that's because it is a 1-to-1 ratio, okay? Silver and chloride react 1-to-1. If it was 2-to-1, then you would have a 2-to-1 ratio of moles of this to moles of that. The nice thing about this unit, though, is it is all going to be 1-to-1. Okay. Because I think it's only really silver chloride that we do a titration for in this unit. And do you remember we were looking for moles of chloride in the original solution? So once we know these moles of chloride and we want to find the concentration of chloride, what volume should we use? Should we use the mixture or should we use the original solution? The original solution. How much chloride is going to be left once we've mixed the two reagents together? None. Good.
The flask. In most titrations, if the proper indicator is used and the technique is good, the equivalence point and the end point are very close, and they can be assumed to be the same point. Once we reach the end point, we must stop adding silver ions to the beaker. This is because we want to know exactly what volume of 0.1 molar AgNO3 solution was needed to just react with all of the chloride ions that were in the sample. We record the initial reading of the AgNO3 solution in the burette just before we start the titration.
Do we need to go back? Yes. I'm like, hang on, something happened really quickly there. Not that one. I guess I press play and then...
Chloride ions that were in the sample. We record the initial reading of the AgNO3 solution in the burette just before we start the titration.
Are we good?
Then we begin the titration, adding drops very slowly while swirling the flask. As soon as the endpoint is reached, we close the stopcock, stop the titration, and record the final burette reading of the AgNO3 solution.
I'd also like to do this titration. It's kind of a fun one. Maybe we'll get 2 labs in here. We'll have like a little lab party. And then we'll move on to the 2 hardest units. Woo! Okay.
The difference between the final burette reading and the initial burette reading will tell us the volume of AgNO3 solution required to reach the end point of this titration.
Once you've got that written down, we're going to do the practice problem on page 86, but cover up page 87 because the answer's on there and you don't want to like accidentally like copy the answer from there because I want to see what you guys record for your volumes. Okay? So cover up page 87, do the practice problem on page 86 for recording your volumes.
Wait, we learned about this.
Yes.
But I forgot.
Yes. That's why we're doing it again.
I need to go about it.
I'm seeing lots of correct sig figs. That's good. I am seeing lots of measurements that are missing something. So think about what your measurement might be missing. Yes.
Where's the
Oh my
first?
God, you're right there.
Where's the measured it? No. So 10.4 is the initial. Really, it's a 10.4. Where you right? 9.6, bro. Where you 9.6 from? Oh, it goes from 9 to 6. Oh, I know it, yes. It is.
Yes. When I say no, I don't mean the numbers wrong. Oh, yeah, you're missing something. Yeah. When I say no, I mean you're missing something. Mhm.
Oh.
Mhm. Yes. Well, look, if you look at the bottom of the distance, are you about halfway? Sorry, past halfway. You're about halfway, sitting up. Yeah. Okay, so we're gonna check over your things. And I'm gonna zoom in here because I can do that. Isn't that nice? So I'm gonna look at this and I'm gonna say I have, and hopefully you remember that these things read down, so it's gonna be 9 point something. This is 9.9, 9.8, 9.7, 9.6. So we're just past 9.6. Are we halfway? No, so we're going to be somewhere between 9.6, 60 and 9.65. Yeah. So like 9.62, maybe? 6.2, 6.3. Either of those would be good guesses. You could even do a 9.61. Any of those would be fine. What's missing from my measurement? Milliliters. Okay, so we've got all our digits plus that one uncertain digit. On our next measurement over here, this is 24.5, 24.4, 24.3, 24.2, 24.1. So we're at 24.1. And then that looks about halfway to me, right? 1.5, you could say 24.14. Anything in that neighborhood would be good. Okay, and don't forget your milliliters. When you do your calculation, don't forget to have milliliters in the calculation. You can only write it once if you want to by using brackets. So we would have the final volume, 24.15, minus 9.62 milliliters. Or you could write milliliters after each number. Either way is fine. And we would get 24.15 minus 9.62 equals 14.53 milliliters. Is good? Okay, excellent. There's our answer to the practice problem. We're not going to worry about the uncertainties. You can just ignore that. So steps to solve the titration problem. You need your, this is what we called step 0 last time, but write the balanced precipitation equation. And usually for titrations, we use the net ionic, because often what they'll do is they'll give you something like AgNO3 plus Cl minus. And do you see how one of them has the spectator attached and the other doesn't? So why don't we just get rid of the other spectator as well and just make it clean and tidy and not confusing? Okay, so usually we're going to use the net ionic. Okay, there's a whole bunch of stuff here. I would say just find moles of known. This is step 0. Step 1, find moles of known. Find moles of unknown. And then step 3 is find whatever. I think those are better steps than what's up there. Because it's just more straightforward. It's like find moles, find whatever. Is good? Okay. Okay. So I would like you to do, ooh, that one's fun. How about question? Actually, no. You know what we're going to do? We're going to carry on and then you can come back and do it later. Now we're going to go through all the different problem types, all 5. Okay? So this is on page 89. So we have solubility to KSP. We have KSP to solubility. We have Q, will it precipitate form. We have max-min problems. And then we have titrations. I think I should do this at the beginning. I think I should add this in. Add in. For all types 1 through 4, you will be writing which two things? The SEE and the KSP. For the two where it mentions precipitates, what will you be doing? You will be either writing the precipitate or identifying the precipitate. You can write the precipitation equation. ID the precipitate. You'll have to do that first. And then finally, in titrations, for titrations, balanced equation, find moles, find moles. So that seems very cryptic. So let's unpack that. So type 1. These are dump and stir. We are given the solubility. Let's find the KSP. What is solubility? Tell your partner. What is solubility? It is the maximum concentration of whatever our low solubility salt is. It is the maximum amount of solute that can dissolve in a given amount of solvent. And so if we know that, if we know the concentration of AB, because we were given it, can we find the concentration of A and the concentration of B? Yeah. Okay. So basically, you're going to find the KSP and calculate the KSP. That's what is going to say in the question. All right. So that's how you would recognize this. You would write the C, you would write the KSP, you would find the ion concentrations. Because this is going to be a dump and stir type problem, they're going to say concentration of AB is, or the solubility of A2B is 0.001 molar. How would you find your ion concentrations if you know that? Pardon me? Yeah. And then you just do stoic. Absolutely. Yes? Whoops, that's backwards. That would be the 2, and that would be the 1. So that's pretty straightforward. And then you'll end up with, if you have an AB salt, KSP is going to equal x squared, where x is the solubility. You can use this in multiple choice questions. If you're doing a written response, write this all out. And then you would write your KSP, you would plug everything in, la la la, and there we go. Read through these questions and see if you can spot the question type. See if you can tell, is this a find the KSP question? Circle or highlight the part that tells you that this is a type 1 question. This is the easiest one to identify, usually. Because, what does it say? Calculate the KSP. What is the KSP? What is the KSP? Yes? Straightforward enough? Okay. If you are interested, I did make an answer key to these questions. But I didn't mean for these examples to be assigned, but in the past I have had students do these. Yeah, all good. And then say, where's the answer key? And so I have made an answer key for it, but these are really just to recognize the problems. But if you're like, I need more problems, you can do, feel free, right? I'm not assigning them, but feel free to do them if you want to. Okay, type 2 is going backwards, KSP to solubility. Do not just look up the KSP. Sometimes people are like, oh, I need to find the solubility. And so they'll look on the table and let's say it was lead iodide. And it says, find the solubility of lead iodide. And they'll go here and they'll be like, lead iodide. And they'll say, the solubility of lead iodide is 8.5 times 10 to the negative 9. Is that correct? No. 8.5 times 10 to the negative 9 is the KSP, which you can use to find the solubility, but is not the solubility itself. Okay, so you cannot look up the solubility on the chart. You can only look up the KSP. This is when you do X, you say let X equal the solubility. And again, it's going to be a dump and stir type question, so that will be proportional. You'll have an X and a 2X, or an X and an X, or whatever the ratio happens to be. Okay. You can tell this is not a maximum or minimum problem because it's not going to say maximum or minimum. Okay, it's not going to say, it's going to mention just one compound. Okay, it's going to say find the solubility, or it's going to say find the concentration of a saturated solution, because that's the same thing as the solubility. It might say what mass of AB will dissolve, which is why it starts to sound a little bit like those max-min problems, right? It might say, what is the concentration of A2 plus in a saturated solution? And then they might even throw in the word maximum to confuse you. What is the maximum amount of the low solubility salt AB that can be dissolved in a particular volume? But remember, this is one compound. In max-min problems, you're always adding how much of reactant CD can be added to reactant AB. So if you don't have a second compound mentioned, you can be like, okay, everything is proportional to the coefficients. So only one compound, everything is proportional to the coefficients. All right. So how do you do this? You write your let statement, let X be the molar solubility. And then, of course, for all of these questions, you write the C.
Wait, you mean product, not
Huh?
how much reactant can be added to reactant?
How much reactant CD can be added to reactant AB? Yeah? So you would have, in a max-min problem, you would have two different reactants, right? And maybe you would end up with compound CB as your low solubility thing. But for all of these questions, remember, unless it's a titration, you should be writing your solubility equilibrium equation and your KSP, and that's probably going to get you at least 1 mark. You know what I mean? Or at least a half a mark, bare minimum. So you're not getting 0 if you write those two things. Okay? Only time you don't do it is when it is a titration. Okay? For this one, again, because it is a dump and stir, when it is dump and stir, you're going to say I got A, B2 in equilibrium with A 2 plus 2B minus, and you're going to have X. Our concentrations are X, X, and 2X, where X is the molar solubility of AB2. And then you just chuck everything into the KSP and solve for X. Once again, in the multiple choice, you can just go straight to the formula. KSP is equal to solubility squared. Yeah? Or for an A2B or AB2, KSP is equal to 4 times the solubility cubed. And that just saves you a little bit of time. So take a look at these questions and see if you could, yeah, sorry. PbCl2 is AB2, yeah? But whereas if you had AgCl, why my pen stopped working? AgCl, that's a 1-to-1. Yeah, it'll just be the subscripts in the compound. Good question. See if you can identify these problems as find the solubility. Hopefully 5 and 7 were really obvious because you have solubility and what is the solubility? For the other two, how many compounds are mentioned in number 4? 1 compound. And it's essentially asking how much will dissolve. So how many grams will dissolve? That's kind of like what's the maximum concentration. And for number 6, it's a concentration of a saturated solution. What is the concentration of a saturated solution? Solubility. It gives you the KSP, although maybe you'll be given that in other type of problems as well, because they also use KSP. So yeah. Anyway, so that's type 2. Type 3, you will be given KSP, or it will be on the table. And you will be given one ion, and you'll be asked to find the other ion or other compound. The other thing about these questions that differ from here, right? Even if I said, what's the maximum number of grams of lead sulfate that can dissolve in water? It wouldn't say what's the maximum that can dissolve in water without starting precipitation. These questions are always going to say to just barely begin precipitation or to just start precipitation. Okay, and we're going to have 2 different salts. So we're going to have AB aqueous plus CD aqueous AD. Let's say AD is the solid and CB is aqueous. So you'll be given these 2. And then you will identify your precipitate. And how do you know you should be identifying the precipitate? Because the question says precipitate. Once you've identified the precipitate, like every other question, what are the 2 things you're going to do first? Write the solubility equilibrium equation. Well, you can do the precipitation equation to identify the precipitate. But once you have identified the precipitate, after that, what will you do? Write the SEE and the KSP, and you'll need ion concentrations. Okay, so it's always like SEE, KSP, ion concentrations. Those are the big 3. And in this case, you only have one ion concentration, so you'll just solve for the other ion concentration. Ignore number 9 for now, we'll come back to it, but take a read through numbers 8, 10, and 11 and see if you can recognize this type of problem. Chemistry is always so funny, I know, right? Laugh a minute. Okay, so in question 8, what gives us a clue that this is a max-min problem? It says maxima, that's good, but also it says both PB2 plus and some other thing, right? We have two things. We are mixing two things. We're going to skip number 9 for now. In question 10, we've got, it says the moment the precipitate starts to form. So that's telling us we're right on that nice edge of precipitation. And we have two things that are being mixed. And then we've got a maximum. That's nice. And barium chloride that can be added to 250 milliliters of 0.5 molar lead nitrate without a precipitate of forming a PbCl2. So we have two compounds. We have BaCl2 and we have lead nitrate. So we're mixing two things. And it says without a precipitate forming. Yes? Okay. So that is type, was that type 3? I think that was type 3. Type 4, Q, will a precipitate form? Unless you are given 0.2 molar concentrations of each and equal volumes. This is usually in multiple choice. But sometimes it could be in long answer. Identify the precipitate, find the ions, write the SEE, write the Q, plug the ions into Q, and solve. So you might be given two compounds, or you might be given two ion concentrations. Okay, either way, you'll just have to say, will a precipitate form? Multiple choice, be aware. KQ can be called K-trial. It can be called trial KSP. It can be called the trial ion product, or it can be called the TIP, which stands for trial ion product. Okay, just watch out for all of those. If it sounds weird, it's probably just a Q. Okay, yeah. See if you can recognize these as will a precipitate form Q questions. Hopefully 12 and 14 should be pretty easy because they say, will a precipitate form? Will a precipitate form? Number 13 is a little bit less obvious, but it says, what will be observed to happen as the ions interact? What are the possibilities when ions interact? Yeah, either it's going to precipitate or it's not. So it really is asking, will a precipitate form? But it's saying to you, do you know what the options are when the ions interact?
You were to get the review package tomorrow.
Yes. You can get it today if you want it. And then finally, titration. Spot the problem. It'll say titration, titrated, titrate. You get the idea. Yes? And this one is totally different from all the others. Do you write a C? No. Do you write a KSP? No. You just write the balanced precipitation reaction. It's going to have a one-way arrow. Usually we're going to use the net ionic form because it keeps our lives simple. So if there's any spectators, get rid of them. Save yourself some grief. You can do these steps, or if we make this step 0, once again, I'm going to change this up a little bit. Step 0 is write the balanced equation. Step 1 is find moles of substance A. Step 2 is find moles of substance B. And then 3 is to find whatever the question asks for. Okie dokie. I think that's easier than what I've got written here. I might need to change this. So there we are. See if you can recognize these as being titration problems. Yes.
I created it.
Fantastic.
Everything, but I didn't sum.
Yeah. It's perfect.
I summed up.
Yeah, wonderful. Thank you. Yeah, great stuff. So how was that? Look, there's the word titration. There's the word titrated. Yes, easy enough. There is a type 6, but this one, let's just read the question. And it says you have a solution in equilibrium with a precipitate of iron carbonate contains, you have the concentration of iron and you have the concentration of carbonate, and it asks you to calculate KSP. This is not one of those problem types we've done, but could you do that? Right? You would say, okay, I would write a C, FeCO3, Fe2 plus CO3, 2 minus. I would have my KSP is equal to the concentration of Fe2 plus times CO3, 2 minus. And I can tell, because it says calculate KSP, that that's what it's going to be. I am given these concentrations. I don't need to find them, so just throw them in there. Yeah? And that's it. You're given ion concentrations. Find the KSP. This type is really trivial. It's hard to find examples. You're not going to see any of these in the problem set, but just be aware that they might come up every once in a while.
Worry about the stability.
Huh?
Don't have to worry about the
No, because you are told you have a solution and these are the concentrations. If you are given a concentration or if you calculate a concentration, never multiply it by 2. If you're like, the concentration of chloride is 0.1, concentration of chloride cannot be 0.2. Does that make sense? If I have 1 pen in my hand, I do not have 2 pens in my hand. Yeah. All right, so there is a problem set here with 5 problems, and that's going to be your homework. There's 1 of each type. Yeah? And I think tomorrow what we'll do is I'll give you, do these ones for homework. And then tomorrow, I think there's like extra practice on these. And I'll give you tomorrow to do some extra practice on these. Right? And there's like 11 of them. And then there's extra practice. Oh, look at that. In case you're like, I want to just practice the crap out of these questions, right? If you get it, though, you don't have to do all of them. Anywho, yes. So yeah, so your homework, and you can start on one of them right now, maybe, is page 94. Page 94. We will start the lab on Monday. So make sure you bring your lab with you. But yeah, I'd like you to have tomorrow to work on it so you can be fully set for the weekend to practice. Your quiz on the math will be, do we want it Tuesday or Wednesday? Wednesday? Sure. Quiz on the quiz on all the math stuff on Wednesday?
I want to get the quiz back before our test.
Yeah. Oh, let's do our quiz on Tuesday then. On KSP and titration math. On Tuesday. There we go. You'll have all day tomorrow to practice. Yes. And you'll have all weekend to practice. You can ask questions on Monday. Quiz will be on Tuesday. I like it. It's good. Okay, awesome.
Oh, thank you. So that was like exactly.
Does anybody want this Tupperware? Nobody wants like random Tupperware from a stranger? Shocking. I'll send it down to the lost and found. It looks like good quality Tupperware. I don't know. You can take it home and sterilize it in the dishwasher.